among them, Stefan Vandoren, our final speaker. He's an expert in black holes, an expert in string theory, an expert in many other things. Used to be the director of the Department Institute for Theoretical Physics. He is current director of the Dutch Black Hole Consortium, and will talk today to us about O'Hare theorems, work together with Vanja and Iris. Thank you very much, and the floor is all yours.
Thank you, Niels. Thank you. Okay, very good. It's really a pleasure to be here and to take up the challenge. I like very much these interactions. They're always fruitful. Over the years, I've been interacting with different communities, for instance, the astronomers, and then I come up with my talk and say, well, Stefan, what you calculate is not observable. But I also sometimes interact with the mathematicians, and I say, Stefan, what you calculate is not well-defined quantitative theory. So I go back. So today I'm prepared. So do ask questions, and I think it's fun, and I always learn something. Also, like the audience. So I want to talk about something that is about black holes. We visited a little bit the O'Hare theorem, which I will review. It's an old story, and there's many counterexamples. And in some sense, my results are yet another example of black hole solutions that actually do have hair in some particular way. I'm going to explain this. But first, some general introductory words, as Niels was saying. Indeed, we have in the Netherlands a Dutch black hole consortium. It's a large grant that we wrote some years ago, and it interplays or it looks for the interplay of different kind of subfields, varying from people building telescopes, instrumentation, people like us, let's say, think about the foundations, quantum gravity, or there's also historians and philosophers, and some fields are joining this consortium as well, and others. The astronomers, and we also have an educational and outreach to society. One of the examples is an exhibition that is currently going on in Boerhaven. Maybe many of you have been already. It's called Closer to the Black Hole, and it has, of course, double meaning. Dichter bij het zwart gat in the Netherlands, closer to the black hole, in the sense that Event Horizon Telescope and other experiments are getting closer and closer to the black hole. But for those who are visiting the museum and don't know anything about it, it also has an educational aspect to bring you a little bit closer to why it is so interesting, what we're studying, and so on. So it's at Boerhaven Museum in Leiden, and it runs until January. So as I said already, kind of in my introduction, I like the interplay of various points of views or angles, and maybe after today I should anticipate today, put another column in that we have different communities thinking about the same kind of issues and problems and objects. The astronomers look at optical signals from Event Horizon telescopes or other kind of telescopes. The first ones that are measuring or doing astronomy about black holes goes back to the observation of Cygnus X1 in the 70s already. It's a long history. It coincides partly with space astronomy or the space research. First satellites going into space. And of course, since like a decade or so, we know more about black holes thanks to the discovery of gravitational waves. They're very complementary approaches. Me, myself, I'm a theorist, and the whole thing about community is to bring these people together and exchange ideas and to speak each other's language. And I think today's workshop is also a nice example of how we can interact and learn from each other. What goes on. So for me, Whereas the astronomer is precisely not interested, well, or hardly interested in how I idealize a black hole. The astronomer is precisely interested in to see the stuff around the black hole, because that's the only thing you can actually observe. I want to put all that kind of stuff away, because it's distraction for me. And if you're just interested in the black hole itself, well, you study the Schwarzschild geometry with the horizon, and so the horizon is, or the black hole is characterized by a horizon with the property that light and signals cannot escape once you're inside, and it is a singularity. And that, for the theorist, is kind of the challenging aspect. So when I try to tell the astronomer that I'm actually interested in the stuff inside, the astronomer loses often interest. What's the point? They ask. And so, okay, it sharpens my mind, and I try to explain better, and so on. Good. So, depending on whether the black hole is just only has mass or rotation, there's some other interesting phenomena that happen. Rotating black holes have not only an event horizon, but also an ergosphere. The ergosphere is interesting. It has never been observed by astronomy as well. Astronomers as well. I can ignore. Well, there was maybe a question online. And so the shape of this ergosphere is kind of depicted here. And it has all kinds of interesting phenomena called the Penrose process, or super radiance if you apply it to quantum fields and so on. And but my talk today are going to be about non-rotating black holes. But hopefully in the future I will extend it as well. So to some extent, if you just study GR and you solve equations of motion, a black hole is rather simple object. You can just write it down in one line. It can be the Schwarzschild solution or the Kerr solution for rotating, or it can have charge. Whether that can happen astronomically, that is a question. It's very unnatural to have a charged black hole, but for a theorist, it's very easy to write down charged solution. And essentially, it's always characterized by three parameters: the mass, the spin, and the charge. And this is what is the essence of the no-hair theorem, that if you try to construct exact solutions with all kinds of matter fields, and you're interested in stationary or even static solution, then there's these three parameters characterize completely the black holes, and there's nothing else that you can add to the black hole. The consequences of that are quite drastic. Here on the right-hand side, you see, I think it is the original Penrose drawing about a star collapsing and forming a black hole. And the no-hair theorem is not just a theorem that is useful for a theorist who's trying to solve the equation, but it has actual very drastic consequence about the dynamical evolution of when a star implodes. The star is characterized by many degrees of freedom, and they all eventually disappear into the black hole solution, which is then only parameterized by three parameters. And all the details of the original star are kind of lost during the collapse. It could be by explosion, losing matter, and so on. So that's a little bit of history. The no-hair theorem is actually the start, I would say, of the information paradox. It's already the classical information paradox, because it's very pictorial here. One can say more about it, but essentially it is the property that once you have a black hole, you throw something in, whether it's a chair or a television or whatever, as long as they have the same mass, total mass. Let's do for the moment just Schwarzschild solution. You just change the mass. Then the only thing that after the thing went in, you cannot no longer tell actually what was the only thing that has changed are the quantum numbers of the black hole after it finds equilibrium. So the mass, the charge, and the spin, and you can no longer tell what actually went into the black hole in the past. And so that is the statements about the black holes have no hair, and therefore classically the black hole cannot have any entropy, because I like to think of entropy as microstates. But if you think of it just in terms of general relativity, there is no states, there's just 3 quantum numbers, and the entropy is just equal to 0. Of course, that we think of it, although the final resolution is maybe not yet known, and the different kinds of entropy. This picture, of course, we now know that there is Hawking radiation, and one way or another there's entropy, and we believe that information is not lost, or at least many people believe that, but there is still not a final word has not been said about this. So it was work by Bekenstein, who actually, Bekenstein was a student of John Wheeler, if I'm not mistaken. And, there was a lot of interaction between Wheeler and Bekenstein, as we always call it in Eric's talk, about the no-hair theorem as well. And in the 70s and early 80s, even in the 90s, this no-hair theorem was sharpened and sharpened. But there were also some counterexamples. In current days, to put this in a more modern perspective also, people are trying to test the no-hair theorem with gravitational waves. So we have 2 black holes, and they are merging. And there's 3 phases: the in-spiral phase, the merger, and the ring down. And the ring down is when the final black hole that comes out of this merging is finding equilibrium. It resonates a bit if you want. And there are some frequencies associated to this ring down. And these frequencies, there's many quasi-normal modes, they are called. And if the no-hair theorem is correct, one should parameterize these wiggles here in the equilibration. It should be possible to parameterize all these frequencies that you find in this signal by only 2 parameters, mass and spin, assuming there's no electric charge in the here. And if you find a signal here, which you can no longer parameterize with frequencies that only depend on 2 parameters, then you have found a violation of the no-hair theorem. That's interesting, because then something's going on. What is the explanation? Was there a mistake in the proof of the no-hair theorem, or is there some one of the assumptions not satisfied, or is it a signal of new physics that goes beyond general relativity? So this is kind of why I got also interested in this topic, because it might connect finally theory with observations. So what precisely was it that Bekenstein proved? Well, there's quite a history of this topic itself, and I'm probably not doing justice, but in essence, it is the following. If you try to couple here, I do have some formulas, but it was okay. But if you couple gravity to, for instance, a scalar field and a potential, can be a mass term for the scalar fields, then Bekenstein proved that if you want something static or stationary, and with relatively mild assumptions on the potential energy, such that there is not too much, it goes into the energy conditions, of course. So with some mild regularity assumptions on V, then and regularity of the scalar field at the horizon, then there's actually only one solution possible. Namely, that is the Schwarzschild solution or the Kerr solution, and the scalar field is trivial. It can be 0 or constant, but if there's really a non-trivial potential, then the scalar field must be actually 0. So that is the, let's say, mathematical statement about the no-hair theorem, which you can prove with these assumptions. And so there is by now quite a bit of counter examples, because here there is a canonically normalized scalar field, and you could take more than one scalar field and put something in front of this thing here, what depending also on the scalar fields. And there was been the discussion about primary and secondary hair, and I'm not going to go too much into that, but just to say that there's some history of this topic here, and you can cook up some weird potentials that are, depending on your taste, natural or unnatural, and then you can violate it as well. Or if you couple two non-abusively engaged fields, which we know from the standard model, you can also find ways to go around the Noether theorem. And so, well, depending on your interest, I can give more details or references. But I'm going to stick to this kind of class of models, but I'm going to change a little bit the gravitational sector. And so, what I'm going to do is to start from a model where I start with Bekenstein's model, but I add something to it. I add something which contains some new ingredients. First of all, here there is something that is called the Gauss-Bonnet curvature. And the Gauss-Bonnet curvature is something that is no longer second order in derivatives or read. It plays no role in the low energy effective physics, but it is a little bit beyond the low energy, the first step beyond low energies. And so that means that for low curvatures, for instance, it's curvature squared, the curvature is low, it's probably not important. But when the curvature gets a little bit higher, that can be non-trivial effect. This term can play a role. So that's what's basically said here. If you know the geometry, the Gauss-Bonnet term is quadratic in the Riemann curvature, quadratic in the Ricci curvature, and quadratic in the Ricci scalar, with well-defined constants in front of it. And why are these constants important? Because of the mathematics. If you take this term here, you write down the field equations, it's actually still second order in time derivatives. That means there is a well-defined Cauchy problem, and we can make calculations. Still higher derivative in spatial derivatives, but we can manage that. In fact, if you, I've written here a f of phi, some new function depending on the scalar field. And if you drop that, then this whole thing is a total derivative term and it doesn't contribute to the dynamics. So the whole point is to let the scalar field interact with gravity, not only through the metric here, but also via the Gauss-Bonnet term. And then this problem becomes non-trivial, yet tractable for a theorist, even though it's going to be numerics at the end of the day. So the potential that I'm going to choose is a simple potential, just the one that Bekenstein also started from, just a simple quadratic mass term. And this function here, there are basically two kinds of sets of solutions you can do. You can write down something polynomial, phi squared, or even something linear, or what people also sometimes do is something exponential. And these have similarities and differences, and for today's talk, I will just stick to the exponential. If you ask me why did you choose that, well, there comes my string theory background. Very often in string theory, you get couplings like the dilaton that come with exponential corrections. But we also looked at linear terms, phi or quadratic. Many of the initial formula are actually the same. And from the point of view of the Noether theorem, you can choose the polynomial or exponentials. It only changes in detail. Okay, so the mass also sets a length scale, and that will become important. The inverse mass is a length scale, and that's called the content wavelength of this particle, if you want. Okay, so this is my model, and now I have to see if I can find new black hole solutions to this model. And before I present kind of the solution, it's always important, like, okay, what are the scales in the theory and what can we expect? So we have two length scales. I put here also some constants in front. I could have absorbed that into F, but the field phi is chosen such that it has no units, it's dimensionless. And that's why I extract here a constant, which has a dimension of length squared. And that's because this has more derivatives does it work with these derivatives? So the metric has no units, then you compute the Christoffel symbols, you take a derivative, that's 1 over length. And then the Riemann curvature, take another derivative on the person, that's 2 derivatives, so that's 1 over length squared. And then I take the square of that. So this has 2 more derivatives. So I have to compensate this with some Fockling constant, which has the units of length squared. That is important. So that sets a length scale, and that means that that there's a new length scale into the problem. That means we can probably probe new types of physics when this length scale becomes when you start probing these new length scales. And the other length scale in the problem is the constant wavelength of the particle. And so you can, everything I will show has kind of like a 2-dimensional plot. I'm going to construct a black hole solution as a function of these 2 length scales. There's various limits. When you set alpha to 0, then this Gauss-Bonnet term goes away. I should just recover the Schwarzschild solution. And you can do perturbation theory in alpha, because alpha can not be too big. I'll come back to that later. So we can do perturbation theory in alpha, either using analytical methods in perturbation theory, or we can do it numerically, and we have done both. And so we're interested in finding deviations from the Schwarzschild geometry as a power series in alpha, this new length scale. And also for if the scalar field would be constant, well, if the scalar field is constant, then we're back in the node hair theorem. This is the total derivative. It does not contribute to the dynamics or the solution equation of motion. We have to we find back the Schwarzschild solution. But the whole point is to find a solution for which the scalar field is actually not constant. Now, when I take the mass to infinity, that's one of these things that the physicist gets quickly intuition for. When the particle becomes too heavy, it does not contribute to the dynamics, and it should decouple from the theory. Or stated differently, if the scalar field is too heavy, the constant wavelength becomes very, very small, much smaller than the black hole itself, or the horizon of the black hole, and it will probably not have any effect. And we will see that. And as I said earlier, for this Gauss-Bonnet coupling, the equations of motion are still second order. This is very important, but it also raises the following question. I chose here something. I can write down 5 other terms of this type. Well, not 5, but well, maybe 5. Yes, I could change the constants and then say like, okay, Stefan, what is why did you fix to Gauss-Bonnet? Well, because I still can make calculations there. The other combinations are harder, and what you would hope for is that there's some universality. You have to think harder about the Cauchy problem, and maybe you can still do things. But this Gauss-Bonnet term is very natural. It's been studied a lot in gravity. I think you have to be aware that there's other terms that you can write down. And as usual in physics, especially in theoretical physics, there's never a problem of making, or there's never an issue of making problems more complicated. And the question is, can we simplify the model, but in such a way that it's still relevant and capturing the basic properties of the black holes that I will present. And I don't know the answer to that. If I start changing the constants, either you just get small deformations or the picture changes completely. I don't know. Okay, so here is basically roughly the idea of what you should have in mind. So there's going to be a black hole that looks a bit like the Schwarzschild black hole solution. That's the black stuff. But then there's scalar field around it. And the scalar field has a non-trivial profile. And basically you have to solve this equation here. This is the equation of motion. And what we call this here, we call this the scalar cloud. So there's a scalar cloud around it because the scalar field is not constant. And it typically follows a curve like this. So here's the distance. There's going to be some horizon, which is approximately the Schwarzschild horizon. But there's deviations because there's this alpha correction. And then there's a scalar profile that goes down faster depending on whether the scalar field is more heavy and heavy. So in the limit that the field becomes too massive, then the scalar hair will disappear, this cloud will disappear, and the lighter the scalar field mass is, then the cloud here, you see it here, it's a little bit bigger than the cloud here. And so these are basically that's basically the picture of new black hole solutions. And it has been studied before in the literature. It's important for me to say that the massless case has been studied before. We generalized to the massive case. There's a few other papers on this topic. And it's actually an interesting kind of research direction that many people are pursuing. That is to maybe it ultimately leads to kind of gravitational experiments in which we can discover new particles. So that is kind of something that you could have in the back of your mind, like, okay, who cares about the scalar field? Well, it could lead to not just new physics beyond GR, but it could also lead to new particles, maybe. Best case scenario. And so here is, in summary, the properties of the new black hole solution. So we now have a third length scale. We had already two in the Lagrangian, the Compton wavelength of the particle, the length scale of this ghost brunetron. Now there's the size of the black hole itself, the horizon. And of course, there is alpha parameter. It's length squared, so the square root is length. Cannot be too big because you will start violating other kind of gravitational experiments in the solar system and so on. And there's already some bounds on it, how far it can be, how much it can be. And if you take this coupling, I think this is the current bound. We'll work in dimensionless units. We'll have like alpha hat, we can divide that by, here it is, the horizon squared, that's dimensionless. And so you can plot this, and similarly you can make a dimensionless mass if you multiply with the horizon. And then you get the following picture. So here's the black hole, and here's the cloud, and stuff around it. And this cloud has a size, a thickness. And the thickness is a length scale, and that's the inverse mass, it's the Compton wavelength. And indeed, if the Compton wavelength is much smaller than the black hole, all the scale of stuff sits in the horizon. Well, the astronomer says, Stefan, what are you doing? It's not interesting. So you get the best effect if the Compton wavelength is of the order of the black hole horizon itself, or a little bit larger. And that's what is depicted here. So here we took some particular value of the m hat. So that's the Compton wavelength is here then 1.25 times the horizon radius. You can also get, if you take a massless field and the Compton wavelength is infinite, the scalar field spreads out over all the universe. So it becomes so thin that probably is too diffuse to have any observational signature close to the horizon. And that's what I'm kind of after with these gravitational wave experiments. So here's the horizon. And then we find here this white line. And this white line is something that we didn't expect, although there were some papers that have similar stories. Usually we think that once you enter the black hole, in the center of it, there's a singularity. But here there's already a singularity quite close, but still from the inside of the black hole. And the singularity for these choice of parameters is at a little less than the horizon itself. Of course, the curve solution also has other singularities than the one at the origin. So, and in fact, one can do with scalar fields. And the reason why there was no hair theorem is that you can write down solutions with scalar fields in a non-trivial profile, but it becomes singular at the horizon. And here, the singularity, you can push it inside the horizon of the black hole. And that's what this Gauss-Bonnet term does for you. So all the solution is regular at the horizon, and that was Bekenstein's biggest, well, not concern, but it was a criterion of proving the no-hair theory. So if we send the Gauss-Bonnet term to 0 again, then actually this singularity goes to the origin, but the scalar field is going to diverge on the horizon. And we have a physical constraint that at the horizon, we want regularity. Nothing can blow up at the horizon itself.
Is the space-time extendable? What I want to say inside the singularity?
Yeah, I need to look a little bit better into this. We can write down the solution. Well, it's a lot of numerics, but we have the numerical solution also inside here. The question is whether you can trust it there, because you're in a regime where you cannot, curvature becomes strong, and then r squared is, that's probably one of the million terms now, because I can add r to the 4th and r to the 6th. So yes, we can, but whether it's meaningful in our approximation, probably not. But from the outside, it is. Of course, anticipating further on this, having a singularity here means large curvature. It will have an effect on the outside, and that's what I'm interested in. So I want to bring the singularity quite close to the horizon in order to have maximal effect outside of the horizon. The effect will still be small, as you will see, but not a substantial. So here is typically what happens with the scalar field. There's a difference between a massless scalar field and a massive scalar. It's just like Coulomb versus Yukawa. In the Coulomb case, there's a 1/r law, and in the massive case, it's Yukawa, it's exponential. And here you see what is going on in the picture here. So here's the distance, and here is the scalar profile. And you see far away, it goes to 0. Set our the boundary condition. And then we get closer to the horizon of the black hole, which is the black line. And then the scalar field is regular at the horizon. That was our requirement. Then it continues inside. It hits the singularity, the curvature singularity, and the scalar field becomes infinite itself. But that was okay. And when we send alpha to 0 and so on, you will get all the problems that Bekenstein also got. But we have regularity at the horizon. And so you see here some details. We can do perturbation theory analytically in alpha, or we can do it numerically exact in alpha. Okay, stuff changes a bit, and I can say more about numerical things. Not too many, actually. There's where Iris did an amazing job. And then we can also play a little bit with the mass parameters, but we get qualitatively kind of similar pictures. So, okay, if there is hair, it's very important to know, well, how much it is, and also whether there's a bound on it, because if we require regularity, it should be finite. So is there a bound on it? And the answer seems to be yes. Here we can plot the value of the scalar field at the horizon. Here is where it intersects the horizon. And then we vary the mass. And then you see the scalar field. Of course, when the mass gets too large, there's no scalar hair, because that's a no-hair theorem. And then we increase the mass, and we, of course, we drop, the Gauss-Bonnet term becomes important. The scalar field raises. And then it reaches some maximum. At least we could only find it numerically in the massive case. There are some bounds that we could estimate, but the details, I think, for this audience, doesn't matter. There seems to be a maximum amount of hair given the values of m and alpha that we choose. So that's the kind of solution that we have. And from the outside of the black hole, it's a totally acceptable new black hole solution. Okay, this is the stuff you have to solve. Let's not go through it again, but it's a coupled system of differential equations for the scalar field, for the stress level you can compute, the Gauss-Bonnet term, and so on. So we put it on a computer and solve it numerically. You can do that. Or we do a perturbation theory, and the equations become simpler. But okay, that's it. What about the solution for the metric? So we have a scalar field and we have a metric. And oh yeah, I use this formula to parameterize the metric. Here is this quantity GTT e to the A. So we're interested in how A behaves as a function of the distance of the black hole, and also B, if there's similarity between A and B. So here is A, and so here we plot the usual Schwarzschild solution, and it's A is just a logarithm of 1 minus 2m over r, and that's this gray curve. This shows how the metric behaves outside of the horizon. And now we do it with our new solution, the scalar field non-trivial, and then you see, well, depending on what we choose for m, here the red curve is for the massless case, and it goes a bit. It has a slightly different profile, and it has a horizon here. You see that the new horizon actually is a bit smaller than the Schwarzschild horizon. The difference is given by these two, given that you fix the mass at infinity. And then you can take formally the solution further, go inside to the horizon, and you see the singularity happening here. So here A is becoming singular, and here's another example where we took a different value of the alpha coupling constants, and then you see here, well, the Schwarzschild solution, same coding here, and then we see if you make alpha a bit smaller, the position of the singularity is pushed further into the center of the black hole. And of course, when alpha is 0, then that singularity is where it used to be for Schwarzschild. Okay, so one has to actually compute the curvature, because the curvature is something that is scalar. See, if something is singular, it could be a coordinate singularity or it could be a curvature singularity. You have to compute this just like with Schwarzschild. Right? The horizon was a coordinate singularity. But the center of the black hole was an actual singularity where the curvature blows up. So here are the plots for the curvatures coupling. So we computed the Kretschmann scalar, which is r mu nu rho sigma squared, Riemann squared. There's also the Weyl tensor squared that you can compute. And indeed, one sees that the curvatures are actually finite at the horizon. Here is the location of the horizon. And then you go in, and then both Kretschmann and Weyl curvatures actually become singular just behind the horizon, depending on the value of alpha. And here you can compare, again, the curvature compared to Schwarzschild. And you see that if you are very close to the horizon, which is the line here 1, then this is the difference between the Schwarzschild, Kretschmann, and the new solution. Then very close to the horizon, the curvature becomes larger, and then it gets a little dip just outside of the horizon, let's say 1.3 or so times the horizon until here. And this is an interesting zone because this is not yet where the photon ring is. That's more like here. You see here the deviations from the Schwarzschild radius. Because the curvature is quite high, it's the curvature that generates also tidal effects. Since the star comes close by, it loses part of its matter, that's tidal forces, and those are generated by the Riemann squared, Weyl tensor squared. And so you see here that there is actually a difference between the Schwarzschild curvature and the Kretschmann scalar, and the Kretschmann scalar of the new solution, and you see that it extends and gets smaller, the difference, and until if you're farther away than 3 horizon, then you don't see any difference anymore between the Schwarzschild solution and the new solution. But somewhere in the region between the horizon and the photon sphere, there are some effects. And then the question is whether it's measurable techniques. Well, of course, it depends on the details. And so we see that the amount of scalar hair actually gets very suppressed when the mass is too heavy. So we want to optimize the effect. And we want to optimize the effect when the scalar field is, when the quantum wavelength is of equal size of the black hole or a bit larger. You can make it as large as you want, but we played with some range, but it should be at least 10 to the minus, well, not at least, at most 10 to the minus 11 electron volt. If it gets heavier, the effect essentially disappears. Now, I don't know how good you are in your particle data mass at book, but this is extremely light. Yeah? The electron mass is something like 500,000 electron volt. This is 10 to the minus 11. Neutrinos were long thought to be massless, but they probably have a tiny mass, but that's of the order of 1 electron volt. That might be the lightest particle that we know of. But this is 10 to the minus, most optimistically 10 to the minus 11, 10 to the minus 21, or you can make it even smaller. And so this is kind of interesting. This is a topic which is well studied. It goes under the name of ultralight bosons. And ultralight bosons might be present in nature for other reasons, dark energy reasons. We need some unknown matter, new particles, maybe small masses that can make up for dark matter. We have light scalars, they're called axions, that might help solve us the CP problem in QCD. So there's motivations from different points of view why the topic of ultralight bosons is important. And this belongs to this class. They're kind of ridiculously low masses, but they might still be useful for dark energy, for dark matter, or for problems related to the QCD axion, CP violation, etc. Okay, the question is whether, well, if that is the case, is that anywhere near observational signals? Who can measure these small masses? Well, not with particle accelerators and so on. Well, maybe you can, but we have not found them in any process so far. But these masses, they can also be converted to frequencies by just multiplying the C. Mass is just inverse length, and you get a frequency. Now, if you think again about my original motivation of merging black holes, then the black holes will merge and there will be gravitational radiation. But there will also, since the scalar field was placed as part of the dynamics, the scalar field can also radiate. And it will radiate with certain frequencies. And the characteristic frequency scale is this kind of frequency scale here. Those are frequency scales that are actually possible to measure in LIGO, Virgo, cardiac kind of observation. So there is already kind of possible sensitivity in a particular range of windows, but so far, of course, we have not done enough experiments here, or we have not seen anything yet. And so it's not completely impossible to confront this to observations. That is basically the message. I should keep a little bit of eye on time. How am I doing? It's 4:45. Yeah, maybe not going too much into detail. I made some comments about the photon sphere because the curvature was a little bit different than the Schwarzschild. So you can take the frequencies. If you have light encircling the black hole, it goes with orbital frequencies. These are the radial on the photon sphere. Light has to travel with given frequencies. And that frequency will be here at the photon sphere. If I compare the frequencies of the photon sphere in the Gauss-Bonnet theory, compare it with Schwarzschild, I get deviations which are 10 to the minus 2 at best or smaller. And at this moment, you cannot measure this. But astronomers nevertheless were kind of intrigued, like, hey, okay, well, maybe who knows, but at present, no. But, so I think it's worthwhile pursuing this. And yeah, since I have some backup slides, but that's maybe more interesting to have some kind of discussion. So in kind of summary, we are not the only one, but there is new types of black holes that people are constructing by adding higher derivative operators, having modifications of general relativity. And we have a nice solution. It's still numerical though, so it is a scalar hair. And the scalar hair that you could circumvent the no-hair theorem. There's already many counterexamples, but that's not too big of a big deal. But the implications could be that there is an imprint of this in gravitational wave signals, and there can be tidal effects that people are interested in. But in principle, it could also lead ultimately to the discovery of new particles. So of course, you can really measure the effects of the scalar fields. Then the conclusion can only be there are new particles exist, ultralight bosons. They are wanted for all kinds of reasons, dark matter, CP violation. And so these ultralight bosons have also been studied a lot in within the context of GR, but in the context of the Penrose process or superradiance effect. Because if you have ultralight bosons, then they can enter the ergosphere and create radiation by itself as well. And that has a story there that has been studied a lot as well. And so that's another kind of research direction where these ultralight bosons are studied a lot. Okay, maybe I should maybe end here and see if there are some discussions, and also make comments about only the sitter, CFT, and that space holography. That's a little bit of a different story, but I'm happy to take any questions.
Thank you.